Hi AP Stats, this is lesson 1.2, displaying quantitative data with dot plots. Quantitative, remember, is numerical, so like how many siblings do you have, how old are you, okay? Dot plots. Each dot represents an individual data value. Brian and Jessica have decided to move and are considering 7 different cities. The dot plots below show the daily high temperatures in June, July, and August for each of these cities. Help them pick a city by answering the questions below. Here we see a city that's relatively warmer. Okay. Here we see a city that's relatively cooler, somewhere in the middle, a little bit more spread out, a little bit more condensed, except for one cold and one hot day. A bit more in the middle here, but then with a few days that are steadily hot, and then few days that are steadily cool, and again a chunk in the middle. Okay, what is the most important difference between cities A, B, and C? A, B, and C. Notice that it looks like the exact same graphic, just slid to the left and center. Okay. So A, B, and C have the same shape and the same spread, but A center is a little bit higher, B center is lower, and C center is lower yet. And if I refer to center and the shape and spread being the same, then when I refer to the center, I'm referring to the whole thing being moved left or right, the left sides, right sides, peaks, valleys, all of it, okay? And so I could say the center of A is higher, then B is in the, a little bit lower, and then the center of C is lower. Center of C is lower, and B is lower yet. Okay, so different center or location. They have similar shape and spread. What is the most important difference between cities C and D? Here's C, here's D. Looks like the center is about the same. The most important difference, though, is the spread. Okay? The difference in spread is the most important difference. City C has less variety of temperatures, centered at about 80 degrees Fahrenheit and anywhere between 65 and 95 degrees Fahrenheit. City D center is also about 80 degrees Fahrenheit, however, it includes values from 60 to 105. Okay. What are 2 important differences between D and E? D and E, well, we can't much say that the min and max are much different, but everything else in between is much more condensed in E than it is in D. So we have a difference in shape. E has outliers at the min and max as the same min and max as D. However, when we omit the outliers, E has much less spread and about the same center as D. So E has much less spread when we omit those, and it is mound-shaped, and D has generally much more spread, and it is more uniform. 4. What is the most important difference between cities C, F, and G? Shape. C is somewhat bell-shaped, where F is more skewed right, and G is more skewed left. Okay, and I do have those skews listed correctly. You'll see how we describe skew in just a little bit. When describing the distribution of a quantitative variable, what characteristics should be addressed? Shape, center, and spread should be addressed. So should outliers. Okay, shape is something like what I have below. I have 6 different descriptions of shape, maybe 7. Center is median or mean. Spread is called IQR, interquartile range, or standard deviation, or 2 measures of spread. Outliers, we have a 1.5 times IQR outlier rule. And be specific, point to specific intervals or data values when you're describing a quantitative variable, and look at overall patterns, and don't let minor ups and downs worry you. Briefly illustrate the following distributions shapes. Okay, symmetric is sometimes bell-shaped or uniform. Symmetric just generally means that the left side equals the right side, and the phrase roughly symmetric is a great phrase to use because we can look at a sample of data and look at that graph, and we can describe it, and we don't have to worry about little tiny minor deviations from the general pattern. Okay. Bell-shaped is shown. Symmetric doesn't mean that it has to be bell-shaped. Symmetric really just refers to our common understanding of symmetric, that left side matches the right side. Skewed right. This is positively skewed or skewed right. That means that this the skier would ski to the right down the slope. Skewed left, your skier would ski down the left side of the slope. It is negatively skewed. Okay? When we talk about skew, we talk about this maybe being a nice mound shape, but then it's this tail that's kind of making our data values look a little higher than they actually are when there's only a few individuals out here at all. Okay, and a few individuals out there at all, and most of the individuals are on the right here. So it's this tail that's kind of pulling mean to the left here, or mean is being pulled to the right here, and that's why we call it skewed. Okay, for example, let me talk about this. Skewed right looks like the right foot, like how your big toe is here, then your other toes get smaller. Okay, and then skewed left looks like your left foot. Your left big toe is here, then all your other toes are there. Okay, single peaked or unimodal is this one. There's one hump, okay, and that might be skewed, it might not be, but there's only one hump in general. Double peaked is bimodal. So if I was to make an x-axis of the length of hair of all the students at RB, then the right axis, no, the left, sorry, did I say that stuff right? The left axis here is frequency, and the x-axis is the length of hair. Then I would have a peak for short hair, because that would be mostly my people who have kind of like a little short hair, okay? And then peak for long hair, because not as many people have hair in between, but then people tend to have it short or longer. Now, an example of uniform is just flat-topped. So that's if I was to roll a die many, many times and have on the x-axis the outcomes of 1, 2, 3, 4, 5, 6, and then have on the y-axis how often those rolls happened, well, I should have just as many 1s as 2s, as 3s, as 4s, as 5s, and as 6s in a balanced die, or just about. So I should have a uniform graph. And then multimodal is just many modes. Mode meaning where most of the data are. So mode, 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 mode. Okay. Notice we don't worry about little bumps. So try to instead think of your graph as if you could lay a tablecloth over it, or make a smooth curve that generalize the graph. Okay, on page 28 of your textbook, there's a little description of Old Faithful. The more time that lapses between eruptions, the larger the eruption is, and sometimes it tends to have two different eruption kind of periods. A smaller eruption that happens after, 90 minutes, and then a larger eruption that has a gap of about 2.5 hours between eruptions. Something like this is the situation. You can refer to the page for better values of the gaps between eruptions. Most of the eruptions fall in those two categories then, a 90-minute gap or a 2.5 hour gap. Okay, so therefore it's kind of bimodal, where the when the eruptions are occurring and after how much time. Okay, all right. Okay. What are the 3 most important things to remember when you are asked to compare 2 distributions? Use comparison words. You must include a comparison word. Longer, greater, shorter, fewer, more, less. Okay, smaller. So the spread is greater. The spread is less. The center is higher. The center is lower. Okay. Socks. Shape, center, spread, and outliers. Include values to substantiate your claim. The mean is higher, around 80. The mean is lower, around 60. Use context. the temperatures in Boston seem to be more variable than the temperatures in LA. Okay? Alternate example, energy costs, top versus bottom freezers. How do the annual energy costs in dollars compare for refrigerators with top freezers and refrigerators with bottom freezers? The data below is from the May 2015 issue of Consumer Reports. Top freezers, bottom freezers, and this is called a parallel or a stacked dot plot, just like my temperatures plots were on 2 pages back. Okay, stacked or parallel dot plots, where I use one x-axis and I use it for all the plots so that I can make comparisons. The typical median energy cost for bottom freezers is greater, okay, because the median would probably be somewhere around here-ish, and we don't even have any values that high on the top freezers. The typical median energy cost for bottom freezers is greater than it is for top freezers, with midpoints at 69 degrees and at 56 degrees. Why is that degrees? Should be $69 and $56 respectively. There appears to be a higher outlier with a cost of $142 for bottom freezers and none for top freezers. There is much more variability or spread among bottom freezers. The bottom freezer distribution is skewed right and possibly bimodal. Okay. Then maybe like another mode here and here. Okay. While the top freezer distribution looks roughly symmetric and unimodal. Okay. What is the most important thing to remember when making a stem plot? Include a key. Put only the leaf on the outside, the 1 digit long. An alternate example. Which gender is taller, males or females? A sample of 14-year-olds from the United Kingdom was randomly selected using the Census at School's website. Here are the heights of the students. Make a back-to-back stem plot and compare the distributions. Male, here's all their heights. Female, here's all their heights. And here we go. If I have a male that's 154 centimeters tall, then I need to include 150 here, and then only the 4 goes out there. And in a way, this is kind of resembling a dot plot where I can see all the individuals, okay? And instead of just a dot though, I have a numerical value, which is even nicer because it's more information. And it still creates this nice visual of stacked values. Now, I should be lining up my stacks just with equal spacing, and it almost looks like I started getting just a little more smushed in with my females and still keeping a nice spread out with my males. However, ideally they would be the same. And we would want, though, the most important part of this is to, in your stem, include all of the digits of the number except the very last 1. And in the leaf goes the last 1 digit in the ones place. So 150s, 160s, 170s, and 180s. Next decision that was made was to split up the stems and to use split stems and to break up the 150s, 160s, 170s, and 180s. And this is 150 to 154, and this is 155 to 159. And this is 160 to 164. This is 165 to 169. 170 to 74, 75 to 79, 80 to 84, 85 to 89. Why would we do that? We do that to be able to see a little bit more shape and curviness. We do that so that we can not just have 4 stems, 150s, 60s, 70s, and 80s. And in that case, it would just look like a bubble of information, and that would be it. But here I can see it maybe a little bit more of a tendency for skewness or for bell shape, okay? And yeah, it just allows me to be able to pick out those details, so of shape. Shoot for about 7 stems then. If we only had 150s, 60s, 70s, 80s for the stems, that would be 4 stems. That's too few. 7 stems is about perfect. So we need to split stems because 150s, 60s, 70s, 80s is too few. Splitting allows us to better see the shape. You must include a key with a stem and leaf plot that's very commonly forgotten. Then we compare the distributions. Male heights are roughly symmetric and unimodal or bell-shaped, while female heights are skewed left. The skier would ski left. The typical center height of a male is greater than a female, median of about 167 versus 163. There is much more variability in male heights than in female. There are no apparent outliers in either gender. Now, folks, we know that if we had many, many more data values, that we shouldn't really see more variety in one gender than the other, maybe. But what we do see here in this data is that there's more variety and more spread in the male than in the female. So I'm just referring to this data exactly when I say things like that. Okay. The following table presents the average points scored per game, points per game, for the 30 NBA teams in the 2012-2013 regular season. Make a dot plot to display the distribution of points per game. Then use your dot plot to make a histogram of the distribution. So here's just a data table, not a frequency table, because all I have is every single team and their points. Okay, so I'm going to make a dot plot. And then after I have this dot plot, I'm going to make a histogram. The first time you make a histogram, it's a lot to pick up on, so let's go slow and talk about all the qualities of a histogram. So we're going to first group the values into bins of equal width. Just like a stem and leaf plot, I want about 7 bins ideally. Okay, so I'm thinking, how do I go from about a 93-point minimum to about a 106-point maximum and include about 7 bins? Well, I see from 93 to 103 is 10, 11, 12, 13 total point value difference between the min and max, 13 points. And if I want 7 bins, I can make my bins of about 2 points each. So I will put those data values in the next highest bin. Oh, sorry, I'll talk about that in a sec. I will start at 93 at the minimum, so I can include these point averages, and go up to 107, counting 2 at a time. Then that gives me 7 bins, which is ideal. Having 8 or 6 is also good. You don't want to have 10 or 4 bins. Okay, then I start plotting these. So 98.0 went over here in the 98s. 96 went down here, 96.5. And I created this dot plot, right? Well, now I need to take everybody from 93 to 95, but not 95.0. 95.0 will go in the next bin, but everybody up to 95. So I include 1, 2, 3, 4, 5, 6, 7, 8, 9, these 9 teams in this first bin from 93 to 95 points. Then I include this first team in 95, 1, 2, 3, 4, 5 in the next bin. And I keep counting. Now for anybody that was exactly on the cutoff of like 95, 97, 99, they get rounded up into the next bin. So like for a team that's exactly 93, they get put into this bin. If a team was exactly 107, I would need an additional bin. Okay, so what do you do with the boundary values? Put these data values in the next highest bin. A 95-point average for a team gets put in the 95 to 97. A 97-point boundary value goes into the 97 to 99 bin. Okay? All right. Describe the distribution. Talk about SOCs. Shape, center, spread, outliers. The distribution of points per game for these 30 NBA teams, context, you need it or you'll lose a point, is skewed right, shape, with a center, between 97 and 98 points per game. The spread is between 106.1 minus 93.2 is 12.9 points per game. There are no high or low outliers. Outliers, shape, center, spread, outliers. Okay, and context. Why would we prefer a relative, meaning percent, frequency histogram to a frequency histogram? A relative frequency histogram makes it easier to compare distributions, especially when the number of individuals is different from one distribution to another. For example, comparing distributions of GPAs for this class versus the entire school. If I just had counts and I had two histograms side by side, it'd be vastly different to compare those y-axes. But if I did it out of percent on the y-axis, then I could really make some comparisons. What is the difference between the bar graph and the histogram? A bar graph, the categorical variables are on the x-axis. It uses something called bars, and there's space between the bars. For a histogram, we have a quantitative variable on the x-axis, meaning it's numerical instead of categorical. Categorical would be like all the colors of cars that you see driving on the highway, and then the frequency of them on the y-axis. Quantitative is like all the mileage of the cars on the highway, and then the frequency on the y-axis. We don't call them bars, we call them bins, but they look the same darn thing. They are bars, if you will, that rise upward to the sky, okay? But a bar graph has space between, and a histogram does not. Your bins are right next to each other. Okay. All right. Cool. On a histogram, also make sure you label, title, and scale, okay? Making a generalization of approximately where the bars go and not labeling is incorrect. Okay. What will cause you to lose points on the tests and projects? A very common mistake, making a histogram with observation numbers on the x-axis and values of the variable on the y-axis. Remember that your variable always goes on the bottom, and then frequency or percent goes on the y-axis. This is called a histogram, and then other ones are called a relative frequency histogram, where you have, instead of frequency, you have relative frequency, which is percents. Okay, thank you for joining.